Hello and welcome once again for another ES340 example problem video. So this is engineering thermodynamics, and we have a piston cylinder assembly here. You can see that we have heat coming out of it. We have work being done by the paddle wheel on the air that's inside of here. The air is doing work on the piston. And we have some initial and final data here. So let's read what the whole problem says. A piston cylinder assembly fitted with a paddle wheel, which we already saw, contains air. Okay, so that's air in here. Initially at P1 equal to 30 pound force per inch squared, T1 equal to 540 degrees Fahrenheit, V1 equal to 4 cubic feet. The air undergoes a process to a final state where P2 is equal to 20 pound force per inch squared, V2 is equal to 4.5 feet cubed. During the process, the paddle wheel transfers energy to the air. That's this part right here. In the amount of 1 BTU, and there is energy transfer from the air by heat in the amount of 12 BTU. So assuming ideal gas behavior and neglecting, this is going to be a key part, assuming ideal gas behavior and neglecting kinetic energy and potential energy effects, find first the temperature in state 2 in degrees Rankine and the energy transfer by work from the air to the piston in BTU. Now note, a key thing is that we can assume ideal gas behavior. So what does that mean? Immediately, you should be thinking that means that z is approximately equal to 1. So we'll take z to be 1, and which implies, since it's ideal gas, that we have PV equal to RT. Now for air, refer to table 3.1 in your textbook. Okay, so this is where I'm going to get this value from. And I find that R is equal to R of air is equal to 0.06855 BTU per pound degree Rankine. Okay? Another way we could do this could find capital M in table A1 and take R bar divided by M equal to R. Now you'll find that although these are going to be rounded slightly different, you'll get something pretty close to this 0.06855 if you do that. One thing that we're going to note that we're going to need is that 1 BTU is equal to 778.169 pound force times foot. We're going to need this conversion factor. So if we do that, then R for air is equal to 0.06855 times 778.169 pound force times feet per pound. This is pound force per pound times degree R. Which is approximately 53.343 pound force feet per pound degree R. Now we're given volume in this problem, so we had a bunch of different ways that we wrote this. and we're not giving the specific volume. This equation has specific volume, but V is equal to capital V over M, and if I substitute that in, that means I have P times V over M equal to RT, or PV capital V equal to MRT. Okay, so we can use that. And thus, we can find this is, again, assuming the ideal gas law. You can't always assume that. Sometimes you would have to find, or if we didn't know that this was an ideal gas, we would go to the table and find these values. Okay, so keep that in mind when we're doing these problems. But that means that the mass of the air, if I rearrange this equation, the mass of the air has to be equal to P1 V1 over R T1, and this is going to conveniently have mostly what we want, although we're going to have to convert the pressure so that it's in per foot squared. So this is going to be equal to 30 pound force per inch squared, and note that there's 12 inches in 1 foot. So that means that there's 144 inches squared in 1 foot squared. So we can use that to our advantage. We know that this has got to be 144 inches squared per 1 foot squared. So those will cancel out, and that'll give me something in pound force per foot squared, which will be convenient because that's my pressure here. Everything inside of here was just my pressure. Now times the volume, which was 4 feet cubed, divided by 53.343 feet times pound force per pound degree ranking times 999.67 degrees ranking. So basically this converted from Fahrenheit. Remember, if we don't have a difference in temperature, you have to use the absolute temperature. So we have to convert this. And you can even see that the units here have per degree R, just to remind you that that is actually the case. So degree Fahrenheit plus 459.67 goes to degree ranking. Okay, so that's the conversion. So this gives us that the mass of the air is equal to 0.324 pound, assuming I did the calculations right. Now, again, it's an ideal gas, so that means that P2V2 equal to M air RT2, which means that P2V2 over M air times R is equal to T2, and we can substitute this in now. So T2, substituting the pressure values, so we had 20 pound force per inch squared from the problem times 144 inches squared per foot squared. That's just to get it into pound force per feet squared. That conversion times 4.5 feet cubed divided by 0.324 pound. That's my mass of my air times my R value, which is 53.343. I just have to remind myself of the units here. Pound force times foot per pound times degree ranking. Okay, so that's my T2, and I get something that's approximately 750 degrees ranking after rounding. So that was part A. Now for B, we have to jump to our energy balance equation. So I'm going to just say that delta E is equal again to delta KE plus delta PE plus delta U, and that's got to be equal to Q minus W. Well, these go away because of the problem said we can ignore those. So this just means that delta U is equal to Q minus W. And what we're looking for part B, remember, is we want to know what the work is that's being done. So that just means that W has to be equal to Q minus delta U. Okay, now we have two sources of work. Remember that we have the work of the piston, the work that's being done on the piston, and the work that's being done with the paddle wheel for the air. Those are our two sources. So that means that the work that's being done on the by the air on piston, obviously it's expanding, so the that's going to be a positive value, plus the work that's done by the paddle wheel, which is really actually minus the work done by the paddle wheel, is equal to the work. That's what W is going to be. So I'll just say W, just to shorten this, that's going to be my W piston minus W PW is equal to Q minus delta U, capital U. And we know what the work was done by the paddle wheel. So this is work of the piston, work done on the piston. Is that what was asking for, actually? Yeah, sorry, this was the work that is done by the piston is actually what we're looking for. So this is the work done by the piston, has to be equal to Q minus delta U plus the work done by the paddle wheel. Which is equal to, well, we were given Q, so we know that Q, remember, was going out from the air. Air was heating the surroundings, and so the work was heating the surroundings, and that means that we had actually minus Q, right? When the sign convention tells us that should be minus, so this should be minus 12 BTU minus delta U. And the work done by the paddle wheel, well, actually, notice that it was given to us as minus 1 BTU. That's what the work is being done by the paddle wheel. In other words, the air is doing work on the paddle wheel. So this is going to, oh, we already took care of that sign, sorry. So this is going to be plus 1 BTU. Okay, so we've taken care of all of our signs now. And that means that the work done by the piston is minus 11 BTU minus delta U. Now, how do we find delta U in this case? Well, notice that it doesn't say that we can assume something like that the specific heat is constant or something like that. So now we're going to have to go to the tables. And basically from table A22E, because that's our table for air. Yes, there exists a table for air. What we find is at T equal to 740 degrees ranking, U is equal to 126. And just go to the table and make sure you understand what's going on here. 0.51 kilojoules per kilogram. And at T equal to 760 degrees ranking, U is equal to 129.99 kilojoules per kilogram. So we're going to have to do an interpolation because we wanted something that was like 750 degrees ranking, right? The nice thing is that in this case it's exactly halfway in between, so you can actually, for a linear interpolation, you can actually just take the mean in this case. This is going to be my shortcut. But just double check your work. So what we find then is U2 comes out to be approximately, my rounding might be off, but 128.2 kilojoules per kilogram. Now we need another interpolation for the other one, because for U1, because as you'll see, 920 degrees ranking and 2200 degrees ranking, we have U is equal to 158.12, and the other one is equal to 409.78. And so basically we're going to do our linear interpolation. So first we find M, which is going to be equal to 409.78 minus 158.12 divided by 2200 minus 920. And then we can use that to help us with our linear interpolation. So we find that U1 is going to be equal to, well, it's going to be M times, what was the T that we were trying to look for? That was about 999.67, or about 1,000 really. So if you get something like close to 1,000, that's fine. Minus whatever the other temperature was that we decide to use. So we could use 920 if we wanted to, plus 409. Oh, that would have to be plus 158.12. And I get this to be approximately 173.79, 0.8, I guess, kilojoules per kilogram. So delta U, capital U, has to be equal to M times U, lowercase u2 minus u1. And remember, we needed delta capital U to find W of the piston here. And this comes out, if you substitute everything in, the 0.324 pound and whatever, this comes out to be approximately minus 14.752, well, 14.8 BTU. So the work of the piston is equal to minus 14.8 minus 11. This is all in BTUs, which is equal to approximately 3.8 BTU. Okay, that's all that I have for this video. Hope to see you again soon.